Okay, I think this is one of the easier topics to explain personally in Calc 3, okay? And I think it's not very hard to understand at all. Some of the problems can get kind of ugly, but it's not because of the integration. It's because of the boundaries. The boundaries, okay? So today, the boundaries are going to be the easiest part, and integration the hardest part, and even that's not very hard. On Tuesday, when I do the second lesson for this, it will be the other way around. Integration will be the easy part. The boundaries will be the tricky part. Okay? All right, so we kind of need to just start with our objective. Like, what do we really hope to accomplish from this? And it's very, very obviously, from the title, we're trying to find the volume under the surface. So let's draw a quick picture together, okay? Imagine a curve, a surface, in fact. It looks something like this. If you look at it from up above, it just basically looks like a rectangular region, like this. Okay? This is the shadow of the object. So you could say, like, this is not the whole object. This is like the base of the object. Down on the XY plane. Okay? The object itself is this pillar thing. It's like a pillar. Okay? And the top of it is curvy. Try to make a good drawing. I'm not an artist. So I'm going to color the top red. Like that. What you're looking at is a surface, Z, up here at the top. Okay? Just like all the other surfaces we've been studying. Okay, we did, remember that goofy looking sombrero thing a couple worksheets ago? That was a surface. We never measured how much volume was under it. You know what I mean? So what we're trying to find is the volume of this weird object. Okay, it's kind of like if I was here standing in this room, and all the four walls look nice and rectangular, right? I've got four walls around me. The floor looks like a rectangle, and then I look up, and I see that the ceiling is very strange. It's not even flat. It's just like kind of warped looking. Imagine being in a room like that. Everything looks normal until you look up, and you're like, that is a really weird ceiling. It is not flat at all. Okay? Well, does that mean then that we cannot find the volume of the room? Of course not. Right? Of course we should be able to find the volume of the room, but how? Okay, so what we need to do is we need to cut it up. And there's sort of two philosophies on how to slice up this room. Okay? One philosophy is you just look kind of like this at it, and you kind of treat it like a loaf of bread. I don't think I would draw everything, guys, because your drawing will be too cluttered. You know, like on a loaf of bread, right, when you slice it, you get these multiple slices. So maybe 12 slices or 15 slices. Imagine doing that to this room and slicing like this. Right? But not making 12 slices or 15 slices, but rather an infinite number of slices. So what we're doing here is we're turning this into an area question. The area of this sheet in front plus the area of the sheet just behind it plus the area of the sheet behind that one plus the area of the sheet behind that one all together compile to make the full solid. Now we know how to find area. We use integration for that. Don't we? Okay? So we could say, look, what's basically going on is we're trying to find first the volume of a sheet. I'll make the top red just to remind you that that's the top. Okay? But here's the front view. You know, you're looking straight at it. You're actually looking in the Y direction right now. It looks something like this. Right? How do you find the area under a curve? Well, you integrate. So let's say that this is x equals a, and this is x equals b, like that. You would integrate from x equals a to x equals b, and you'd put in these little rectangles, right? Riemann sum. Find the area of all these rectangles. Now remember, the height of this is no longer y, it's z now. it's z. So the height is z, always in 3D, right? So basically you just integrate the z function from a to b dx. Now what that does is it fills in these blue rectangles, infinite number of them, as you know, and gives us the volume of one of many slices of the bread, or slices of the room. So this only provides us with the front sheet. Well, there are plenty more sheets that we didn't find, right? But we can now integrate the sheets together. See, the sheets now stack into the y dimension, working back into the board. So you'll be integrating now to stack the sheets together after getting the rectangles glued, see? So you're going to be integrating now from y equals c to y equals d. So you can integrate one more time. This time in the y direction, so dy. And it's like the first integral was sort of just the first thing you did, right? You collected the rectangles to make your sheet, and now you're collecting the sheets to make your solid. And so the inside, the integrand, is an integral. You see? So let me title this. What is this thing? This is the area of one. Actually, that's not quite true. Let's see. How do I label this? This is actually, yeah, this is the area of one sheet. The full area of one sheet. And the whole integral is the volume of the solid. It's not really a solid, it's just, we're visualizing it as solid because we want to find its volume. It's really the empty space under the surface shell on top. There's no sides, really. But we can visualize it as a solid that we're trying to fill with water. It's the same idea. Is that complicated? In a way it is, because it's all 3D and everything. But really what we're doing is we're using integration to stack these rectangles together to form a sheet. And we're using integration to stack the sheets together to form a solid, you see. This is one philosophy on teaching it. I actually prefer to explain it another way. So bear with me. I'm going to re-explain this whole thing using a slightly different approach. Okay? Some people don't like this because they think it's a little informal. But I love it because it helps students really understand the whole point of integration. So, same drawing. I'll try to duplicate what I had. Rectangular shadow down here on the plane. Some of these sides have to be dashed, you know. These are sort of the walls. And then up top we have a red surface. Maybe I'll draw it a little more visible this time. This is why we use a pencil, right? So we can erase. Something like that, maybe. Okay, I've always liked this explanation better. You can tell me if you like it or not. It doesn't matter to me. You will not insult me if you don't like it. I like to visualize this as a collection of columns. And I don't care where I start. Nobody really slices their bread this way. But imagine right there in the middle of all this large blue and red column is a little purple column. Okay? Now he is a true differential. Like, he is tiny. He's very, very small. Because this is the x direction here, I suppose this distance is dx. It'd be this one down here. But I guess it doesn't really matter which side you label dx. But this is sort of the micro change in the x direction. It represents kind of the little width of that column. And then there's a y dimension here too, isn't there? The y dimension takes us sort of front to back to front kind of. So let's say that this is y equals c again, and this is y equals d over here. So this little dimension here is dy. And if you get the dx and dy mixed up, it's not going to matter. Okay? in this picture. But the height of this thing is not differential at all. It's very, very finite. It's like z. It's an actual distance. And you might argue, well, Mr. Shore, I don't know. I don't think that's really a flat top. I don't think that top is really that flat. You're probably right. It's got some tilt to it. But how big is this thing? Infinitely small, right? So unless we're near like a section of the surface that's vertically tangent, I think that top can be thought of as roughly flat. Does that make sense? Okay, so in the differential case, we kind of ignore slopes, right? We did with Euler's rule too. We've done this before. This is what people don't like. They don't like the informality of the top. They don't think this really is a rectangular solid, because I'm about to write down the volume of this little guy. The volume of this is length times width times height. Right? Think 7th grade. What's the volume of this? Length times width times height. I'm going to write it as z dx dy. Okay? Now, is this the volume of the whole solid? Of course not. I need to start collecting these guys together. So I'm going to go ahead and start integrating. Now I'm treating integration like a tool. I'm just going to slap an integral on here. What does it do? Well, let's say that we do it first from x equals a to x equals b. What did I just do? I just collected a bunch of these little guys, a bunch of these little columns, all in the x direction. I'm holding y constant for a moment. Okay? It looks like I'm over here at y equals 5 or whatever. I'm just going to hold that constant. And I'm just collecting these guys together. So it looks like this. You see? By integrating into the x dimension, I'm forming my sheet from scratch. This is that same sheet we were talking about earlier. In the picture up here, it looks like this. It runs at a constant x, or a constant y value. There's your sheet. I don't even care if it's in the beginning, in the front of the solid, or in the middle of the solid like I drew. It doesn't matter. That's what I like about this approach. I'm just sort of building from scratch. I've got this little column. I just projected them and cloned them into the x dimension. See? And I collected all of them from x equals a to x equals b. Some people really stop and say, Mr. Shore, I don't like how you're just throwing the integral on there with no context. I'm collecting. I'm integrating. I'm putting together things. But technically there's a little bit of informality to it. It is a limit, right? Okay, is that the volume of my solid? Not quite. I need to collect sheets now. So now let's go ahead and collect sheets. I'll put an integral y equals c to d on here. This is the same thing I had up here 2 seconds ago when I explained it with collecting sheets in the first place. But I did this first by collecting columns into a finite sheet. And then I collected sheets to form the solid. So I don't care which approach you take, this is the formula of the day. So here's a question for you. Okay, it's a yes or no question. Do you think it matters which order we collected? Could I have collected all the columns into the y dimension first to form a sheet, and then collected sheets into the x dimension to form the solid? Could I do that?
Yes.
I could. The reason that is okay is because, this is very, very important, listen, the base of this is a rectangle. So there is zero order of operations here. It doesn't matter if you integrate with respect to x first or y first, it makes no difference. On our second lesson, it will make all the difference in the world which one you do first. You can set it up either way, but one of those ways will be too hard to solve. So then we're going to have to learn to switch it back to a different way. In other words, sometimes we're going to have to switch the order of integration, because we're going to integrate 2 times to get this to work. And you'll find it's too hard in one direction, and it's much easier in another. And being flexible, that's going to be the hardest part of all. Okay? And that's why I said there's a boundary issue. We'll see that on Tuesday. Okay, so how hard are these problems? They are not hard at all. Do you remember when you took a partial derivative, you treated y like a constant, and you took the derivative with respect to x? Imagine doing antiderivatives that way. That's all this is. Okay? The idea is when you collect, this is very important, listen, when you collect the columns into the x direction, you are treating y like a number, because all of these these columns have the same y. So when you're doing antiderivative, you will just treat y like a number and integrate. Let's try one. It's really not very hard at all. One last comment before our first example. I do not want my red sheet today to ever go through the plane, through the desk. Okay, let me show you what I mean. I really want to avoid problems like this today, where the red surface hits the xy plane and protrudes through it. You know how planes do. Sometimes planes intercept. If our plane that we seek to find the volume under hits the desk and goes under, we're going to get a negative volume underneath. Okay? In the same way that when a y and x function, right, back in CALC 2, CALC 1, when a function goes under the x-axis, those areas thereafter are all negative. The same thing happens if our sheet comes down and contacts our desk and goes under, we're going to get negative volumes for that underneath part. So we're going to avoid that like the plague today. None of my examples have that at all. So don't stress about that happening. Okay, so my first example is this one. The function is, so find the volume under the surface. Find the volume under fxy equals x squared y for 0 is less than or equal to x, is less than or equal to 4, and 0 is less than or equal to y, is less than or equal to 4. Now, do you have to graph the surface? No, you do not. You might want to just roughly sketch it, but that can be too hard for some students. So all I'm saying is I've already promised you that this thing stays above the desk. The only reason you really want to graph it is in case you suspect it hits the desk, but it doesn't. If you look at it, I'll draw the first one for you. Everything kind of starts at 0, 0, 0, you know? As x grows and y grows, this thing grows. So this surface just kind of comes up and goes up like this, leaving some space underneath it. Okay, so here's your rectangular region underneath. So this is like a big ramp, just comes up. It comes up off the desk. It's like this, guys. Watch my over here, goes like that. Okay, it comes up like that. Alright? It's linear in some directions and quadratic in other directions. You can see there's an expert and a y there. Don't worry about that. But I don't think this thing will hit the desk except at the origin. But we're going to be integrating into the first octant. That means going into the plus, plus, plus realm. So we're not stressing about it. We're going to be integrating from 0 to 4 for x, from 0 to 4 to y, so it's all very symmetric. Okay, so we're going to be going from 0 to 4 on the x, and from 0 to 4 on the y. So this is actually how you set it up. Watch. Let's do the x first. So you go, okay, I'm going to go from x equals 0 to x equals 4. Mr. Shore said that there should be a z dx here, and then we're going to integrate again with a dy there, and this time y equals 0 to y equals 4. But you're going to be solving the inner problem first anyway, so I guess if you just want to do this in 2 stages you can, but I suggest you learn to write double integrals. So write it like this, an integral within an integral. Okay, if we're doing an integral with x as our variable, we're going to treat our y as a number. So you guys know how to find the antiderivative. You're very good at it, right? What's the antiderivative of x squared? Because we really don't care about the y. 1/3 x cubed. What about the y there? Well, he's like a 10. Leave him. Yeah, so we're just going to leave him there. So this is just going to be 1/3 x cubed y. I guess y is a number. What else are we supposed to do with definite integrals? Aren't we supposed to plug in the 4 and the 0? We better do that, right? Now remember, these are x's. So plug them in for x only. And remember, we still have this dy to worry about later. Okay, if I plug in x equals 4, I get 64/3 y. If I plug in 0 for x, I get 0. That's nice. This is my next problem to work on. Now I need to integrate from 0 to 4, and y, of course, is my variable. It's the only variable left. What's the antiderivative of y? Because the 64/3 is there to stay. What's the antiderivative of y? 1/2 y squared, right? Yeah, so we end up with 64/6 y squared, and we're going from y equals 0 to y equals 4. I told you this isn't hard. Only the concept is hard. 32/3, and then there's a 16 minus 0. So 4 squared minus 0 squared. So our answer is 512/3. 512/3. What is it? It's a volume. So let's put units cubed on there. It's a volume because of the dx and the dy and the z. Let me show you real quick. Just look at the units here with me, guys. I've got z, I've got dx, I've got dy. What are the units of z? Let's say everything's measured in inches. Z is actual physical vertical dimension. So let's say that everything's measured in inches. What are the units of z? Inches. Right. What are the units of dx? It's differential in its size, but it's linear measurement nonetheless. What are its units? Inches. Dy, inches. Okay? Or we can say inches cubed. And since we're not necessarily dealing with inches, we'll just call them unches cubed. That was Tristan Hatchell last year. Unches cubed. Units cubed. Okay. So that's not very hard, right? So then they try to make it really hard for you, so they make the integrand tougher, but you guys are so good at integrating, this is so easy for you. All right, so let's try another one here real quick. How about integrating, or let's write the question real quick so we remember the context. Find the volume, and when I say under, I really mean below the surface, above the xy plane. So below the surface, above the desk. You know what I mean? So maybe I should put find the volume between the surface and the xy plane, just to make it really clear what I mean. Okay, so our surface is xy e to the minus 1 minus x squared minus y squared. You might recognize that one. That's almost one that I used yesterday, I think, in my lesson. I think. Okay. The region, the base, the shadow, the bottom, the part on the desk, has corners at 0, 2, 0, 0, 4, 0, and 4, 2. What are we saying? It's very simple. I'm just saying, look, I'm trying to be sneaky and confuse you, okay? Instead of telling you the domain for x and the domain for y like I did on the last one, I'm trying to disguise it a little bit. Where's 0, 0? Right here. Right. Where's 0, 2? Isn't that just right here? Where's 4, 0? Well, that's over here. Right. Where's 4, 2? Well, that's just here. So what is x between, guys?
0.
Yeah, 0 and 4. Right. It's just my sneaky way of saying that. So x is between 0 and 4. But I'm not the only one, okay? Sometimes they do that. They just describe the region. They don't actually tell you that. Why don't they just say this in the first place? 0 is less than x less than 4. What about my y's? What are my y's between? 0 and 2. Right, that's all. They're just trying to disguise it. These are your limits of integration, naturally. Okay, your surface, I don't know, up here, so I don't know. It's becoming less and less important that we draw everything perfectly, right? Pretty sure that this expression is going to stay positive. The z will stay positive as long as I plug in positive numbers. If x is a positive number and y is a positive number, the exponential is always going to spit out a positive number. Maybe small numbers, but positive. So everything's above the desk. The question's clear now what we're doing. We're integrating this function, right, z equals, over these two domains. So here it goes. The rest is mechanical. Integrate from x equals 0 to x equals 4. The function is xy e to the 1 minus x squared minus y squared. The second integral will be on the outside. I'll use green. It's a dy integral, and it ranges from 0 to 2. The rest is mechanics. This integrand is a little tougher, though, isn't it? It's a little bit tougher integrand. Let's see, what kinds of integration tricks have you learned? What kinds of integration tricks do you guys know? Parts, integration by parts, yeah. Substitution. Tabular, right. You have a whole handful. I think this is a substitution problem. Remember, y is a number. Oh, I forgot to write my dx. Mr. Short, that's really bad. Really bad. You guys know how bad that is, right? After a year with me. The dx means we're differentiating integrating with respect to x. So y is literally like a number. If I gave you this problem and y was, 1, you wouldn't have any problem at all with it, right? This would read x e to the 1, or x e to the negative x squared. This is what it would read if y was 1. We'll try to treat y like a number. Can anyone think of a good u sub that would help us here? Some of you are really good at u subs. That's what we need. Let u equal what? Anybody? Yeah, 1 minus x squared minus y squared is a great choice. Because the du is perfect. It's just negative 2x dx. What happened to the y? It's a number, right? So I guess this is like a partial du or something. Don't worry about that, okay? Don't curl the d's. I've never seen anyone curl the d's here. Negative 2x dx. Okay, so negative 1/2 du is x dx. Well, I have an x dx right here. Okay, so I think what I have here is basically a y e to the u du. Y e to the u du. Okay, so our integral looks like this now. Y e to the u du. And then we have the y integral outside it. If you're getting confused by the two integrals, you can stop writing the outer one. Okay, what's the antiderivative of y e to the u? Y e to the u, right? The y is still a number. We haven't done our integration for it yet. So the y is literally a number. The antiderivative of e to the u is e to the u, right? So basically, it's like erasing this integrals on the inside. So here we go. Now we have the 1/2, negative half. I'll put it way out front here. Thank you. You asked where it was. It's right here. Now it's there, now that you mentioned it. Thank you. Okay, so the antiderivative is y e to the u, and I think we owe it where we have to plug in 0 and 4. But these are x's, right? You can't plug those into u. So let's put that u back to what it meant originally. Remember, the u originally was 1 minus x squared minus y squared, so let's write that. So I'm still staring at that inside. This is all I care about right now. Try to ignore other things. I need to plug in 4 for x and 0 for x. Okay, so it looks like this. If I plug in 4 for x, it's going to read y e to the negative 15 minus y squared. And if I plug in 0 for x, it's going to read y e to the 1 minus y squared. Bless you. This is the boring part, though. Okay, you're not going to be able to combine these in any meaningful way, but you can integrate them both using u sub again. Okay? So, on this first one, you want to let u be negative 15 minus y squared. So negative 1/2 du is y dy, and you do have a y dy there. For the second one, you're going to let u be 1 minus y squared, and negative 1/2 du is y dy, and you do have a y dy here. See? So basically, both of these integrals are just negative 1/2, and then it's just e to the u du. These are both negative 1/2 e to the u du integrals, both of these. So they're both going to integrate to basically e to the u. As for that negative half, I can just bring that out to the front. So this negative half and this negative half will make a 1/4. So I'm trying to save a little time here. Both of these integrate to e to the u. So the first one integrates to e to the minus 15 minus y squared. The second one integrates to e to the 1 minus y squared. And then we still have to plug in y equals 0 and y equals 2, as you know. Okay, so here's where it gets a little messy with numbers, but if you plug in 2, you're going to get e to the negative 19 minus e to the negative 3rd. If you plug in 0, you're going to get e to the minus 15th minus e to the minus 1st. So all things said, we have 1 over 4 e to the 19th minus 1 over 4e cubed minus 1 over 4e to the 15th, and then plus 1 over 4e. So sorry to those 5th period where I accidentally had an extra couple numbers in there. What had happened was, I can explain my error. Let me go back a little bit. Right here, when I taught it during 5th period, I had accidentally put my y here. But y dy is replaced with du. So there should not be a y e to the u. So I'll write what I had in class, which was wrong. I had basically, right here, I had a y that I should not have. So it affected my work thereafter, so I apologize for that. Fix it if you feel you need to, or hopefully you got the gist of it all anyway, but that's the end of that. So, then let's just put some units on our answer, and you can see this is pretty much a calculator answer, isn't it? I mean, after all things are said and done, probably kind of wish I'd used a calculator in the first place on this. Okay, so in any case, our final answer is, let me get my calculator out. My calculator is taking a while with this one, actually. In any case, it's units cubed, or as I like to say, inches cubed, about 0.667. 0.667. 124. So not 2/3, but close to 2/3. And remember, the calculator uses approximations, so it's pretty accurate. And that's volume under a surface. Just so you know, our next lesson, our surface shadow, the bottom, the base, will not be a rectangle necessarily. So it could be other shapes, and that will cause quite a bit of extra work for us.